So we defined a splitting field of a polynomial last time, gave some examples. This is the first non-trivial example on the right here. Q adjoin 2 to the 1/3 omega. That's how you read it. That to Q I'm adjoining a cube root of 2 and this cube root of unity. Omega is e to the 2 pi I over 3. This is the splitting field of this polynomial x cube minus 2 over rational numbers. In fact, it's an extension of degree 6, meaning this K is a 6-dimensional vector space over Q. We have seen already that our polynomial fx splits into linear factor in kx. This is the factorization of our polynomial in kx. Right? Because these three things are the roots of this equation. The cube of 2 to the 1/3 is 2. Yeah, but the cube of omega is 1, so the cube of this is also 2, etc. What I want to show is that this is the splitting field, meaning that f cannot split into linear factors in anything strictly smaller. And this turns out to be rather easy in this case. You have k, let's write down a couple of intermediate fields. K, you have q 2 to the 1/3. You also have this extension. And this is a degree 3 extensions because, for example, this is irreducible. X cubed minus 2 is irreducible, so if you take qx mod that irreducible polynomial, that's isomorphic to the field obtained by adding the root. This we have seen before. And this thing is 3-dimensional vector space over Q. So this is a degree 3 extension. And the only thing we have to figure out is that omega is not in there. But omega is not in there, one way to say that is that this is a subset of reals. But this cube root of unity is a complex number which is not in real numbers. So omega is not in here. So this k, if you call this guy m maybe, then k is same as m add omega. Because once you have omega and 2 to the 1/3, you have everything. And now that I know that omega is not in m, I know that this extension, k over m, is non-trivial. But on the other hand, you know that omega satisfies a quadratic equation. Omega squared plus omega plus 1 is 0. So this omega satisfies a quadratic equation over rational numbers already, so over m as well. So that tells you that this extension is at most degree 2. But it's not degree 1 because omega is not there, so this extension is degree 2. Okay. And that tells you this is degree 6. And if you have any sub-extension that already, where this already splits, it would have both 2 to the 1/3 and omega, because once you have all three roots, you have this guy and that guy, then you have this guy and the ratio, which is omega. Okay. That tells you that you cannot split it in anything smaller, and also that this extension has degree 6. So that should serve as a non-trivial example, which is actually very good to keep in mind when we do these general theorems that are coming up. I mean, one should really do lots of examples like this. Maybe we'll have some in the exercises, and we are not nearly going to have time to cover many examples like this. So here's the theorem. It basically says that splitting fields exist, they're finite extensions, and they are essentially isomorphic. So here's the existence part, which is all that we'll prove. That you give me any non-constant polynomial in fx, there is a finite extension k over f that is a splitting field of this polynomial. Sometimes we'll just say finite extension k. It's understood that the f has been fixed. And then part B says that if you have two extensions, both of which are splitting field, then they are isomorphic. So this is the uniqueness. And isomorphic means isomorphic as extension, which, if you remember, means that there is isomorphism, field isomorphism from k to k prime, such that the restriction of sigma to f is just identity. So f fixes f pointwise. So to prove A, you prove first a lemma that there is some extension at least where the polynomial splits. Maybe not the smallest yet, but just the first condition. Remember, splitting field means two conditions has to be satisfied. F has to split in K, and F cannot split in any proper intermediate subextension. So let's first find an extension where this polynomial does split. That's going to be the first lemma. Let give ourselves a non-constant polynomial. Then there exists a finite extension M such that P splits in M. And you do this basically by adding one root at a time in stages. You see, you start with F. If P already splits there, then you're done. There's nothing to be done. If it doesn't, so suppose P does not split, then you take a irreducible factor and you add a root. Let P1 be an irreducible factor. I know that I can go to a finite extension of degree equal to the degree of this factor and get a root. So then you go to this guy. And this is an extension of degree equal to the degree of the polynomial. And in K, P1 has a root, so P has a root. What do I want to call this guy? Let's call it M1. Sticking to my notes here. So in M1, your polynomial does factor. Px is x minus a times some other guy. In mx. So for some polynomial of lower degree. And now if q splits, then you're done here already. Otherwise, again, add a root of q. So if q has a irreducible factor p2x, now I go to m2, which is obtained by adding a root of p2. Every time you do this, you're doing a finite extension, and every time you're getting a linear factor out, at least, maybe more. So after a while, you're going to factorize it completely. That's basically the proof. So you run an induction. And once you know this, the existence part of this theorem is immediate. So proof of theorem Part A, you take some extension where, so I'm given P and I have to find a splitting field. So you take some finite extension where P splits, and then you look at all possible sub-extensions where it does split and intersect them all. And that's going to be a smallest one. So it's sort of not much, just one line. By lemma, there exists a finite extension M over F such that P splits in M. Now let K be the intersection of all sub-extensions where it splits. In which Px splits. And an intersection of a bunch of fields is again a field. If all of them are contained in M, the intersection is also contained in M. If all of them contain F, the intersection also contains F. So you have M, you have F. You know that your polynomial splits here. Look at all the things intermediate where it does split, and then you intersect them all. And that's going to be the smallest thing where it still splits. You can check rather easily. Verify. Px still splits in K, and then once you do that, you know that K is a splitting field. I certainly cannot split in anything smaller because I have intersected all of them already. The proof of the uniqueness, part B, is considerably subtle, and you have to actually think about this quite a bit, and I am not going to go into it right now. You can read in the notes. But I'm going to move on to algebraic closure and talk about algebraically closed fields a little bit and embedding things inside algebraic closures before going on.